Hey, welcome to Models and Agents, episode 21 for March 27th, 2026. Your DE Bomber AI briefing on the models and agents that are actually changing how we build intelligent systems. And no, not those kinds of models and agents. Let's get into it. Today's arXiv drop in cs.CL is especially spicy because it pulls back the curtain on several evaluation practices we've been taking for granted. Three major themes jumped out: serious contamination in depression detection benchmarks, nuanced failures in model pruning depending on task type, and surprisingly large gains from fine-tuning even modest-sized models on domain-specific medical data. The recurring insight across the batch is uncomfortable but important. Many of our current evaluation setups are heavily contaminated by dataset artifacts, prompt regularities, and evaluation shortcuts that don't survive real-world scrutiny. This isn't just academic nitpicking. It has direct consequences for anyone shipping clinical AI, production ML systems, or safety-critical agents. Let's start with the top story, which should make every team working on conversational medical AI pause. A careful analysis of three widely used public depression detection datasets, Androids, DAIC-WAS, and eDAIC, revealed the same systematic and alarming bias. Researchers discovered that models were achieving impressive-looking performance not by detecting genuine linguistic markers of depression in participants' speech, but by exploiting the highly consistent interviewer prompts and fixed question ordering that characterize these semi-structured clinical interviews. When the team trained models on the full conversations, performance looked excellent. But when they restricted the models to only participant utterances, stripping away everything the interviewer said, the decision evidence suddenly became much more distributed across the entire conversation. In other words, the models had been lazy. They learned to listen to the interviewer's predictable behavior rather than the patient's actual mental state. This bias isn't limited to one dataset or one architecture. It appears anywhere you have semi-structured clinical interviews with consistent prompting. The paper makes a strong case that we need new analysis techniques that localize where decision evidence is coming from, both in time and by speaker. If you're building any kind of clinical or mental health AI right now, you should immediately audit your models. Are they actually listening to patients, or are they gaming the interviewer's script? This finding feels especially timely because mental health AI has been one of the most hyped application areas. Papers like this are a necessary corrective. They remind us that impressive benchmark numbers can sometimes reflect artifacts of how the data was collected rather than genuine clinical signal. This theme of contaminated evaluation is driven home even more explicitly in the paper titled "When Consistency Becomes Bias." The authors demonstrate that models can reach strong depression detection performance while essentially ignoring participant language entirely. They simply latch on to the fixed interviewer prompts that appear in nearly identical form across the dataset. Only when the analysis is restricted to participant utterances do the real linguistic signals of depression begin to surface. The implications here go far beyond depression detection. Anytime you're building medical conversation, Ion AI, diagnostic agents, or even legal educational dialogue systems that rely on semi-structured interviews, you need to be asking these same questions about speaker-specific evidence localization. This paper should become required reading for any team claiming clinical-grade performance from conversational models. Shifting gears to model efficiency, the paper "Demystifying When Pruning Works Via Representation Hierarchies" delivers one of the clearest explanations I've seen for why pruning behaves so differently across tasks. The core insight is that neural networks maintain three distinct representation spaces: embeddings, logits, and probabilities, and these spaces respond very differently to pruning. Embedding spaces and logit spaces turn out to be surprisingly robust to aggressive weight removal. The problems only really begin when you apply the nonlinear transformation from logits into probabilities. That nonlinear softmax step amplifies even tiny deviations, and those amplified errors then compound across every single autoregressive step during generation. This explains why retrieval, classification, and multiple-choice tasks often survive aggressive pruning, while open-ended generation quality collapses. The authors even released their analysis code, which is genuinely useful. If you're maintaining production models and looking to reduce serving costs, this paper gives you a proper mental model instead of the usual just prune low-magnitude weights and pray approach that's been circulating for years. On the medical AI side, two papers particularly stood out for showing what's possible with focused fine-tuning. In one, researchers took a 1.2B open-weight model and fine-tuned it on just over 8,500 human-rated titles and abstracts for systematic review screening. The results were striking, an 80.79% improvement in weighted F1 over the base model. On the full 8,277 study dataset, it reached 86.4% agreement with human screeners, with a 91.18% true positive rate and perfect consistency across inference runs. This is a powerful reminder that for many high-stakes but relatively narrow medical tasks, you don't necessarily need frontier-scale models. A well-targeted 1 to 2B model on high-quality domain data can deliver outsized returns. Similarly, another team fine-tuned a Llama 3.1 to 8B on a relatively small Finnish clinical conversation corpus for medical transcription. Despite Finnish being a low-resource language and the dataset being modest in size, they achieved a strong BERT score F1 of 0.8230. The n-gram overlap was relatively low, but semantic similarity was excellent. This work makes a compelling case for building privacy-preserving, domain-specific models, even for languages that typically get ignored by the major labs. Moving over to the agent and tool use side, there's a genuinely practical new system called Model Feature Agent, or MOFA. Instead of treating feature selection as a pure statistical problem, MOFA uses an LLM's semantic understanding and quantitative feature information inside structured prompts to perform sequential, reasoning-based feature selection under real operational constraints. In a true interest prediction task, it delivered accuracy gains while simultaneously reducing feature complexity. It also surfaced high-order interactions that improved online engagement metrics. For notification prediction, it selected compact feature subsets that boosted both accuracy and inference speed. What I like about this work is that it shows LLM reasoning can add real value in production ML systems where labeled data is scarce and you have strict latency and infrastructure constraints. This feels like the kind of agent pattern that will quietly make its way into many industrial ML pipelines over the next year. Another notable tool-oriented paper explores using lightweight LLMs as prompt attack detectors using an LLM as a judge approach. Models as small as Gemini 2.0 Flashlight 001 proved surprisingly effective as low-latency security judges when given structured reasoning chains that include intent decomposition, safety signal verification, harm assessment, and self-reflection. This system is already deployed in production as a centralized guardrail for public service chatbots in Singapore. Interestingly, a mixture of models variant only gave modest gains over the single model version, suggesting that careful prompting and reasoning structure matter more than raw model scale for this particular safety task. In the practical and community section, one paper offers a very clean, controlled study on synthetic rewriting as a quality multiplier for continued pre-training, this time in Portuguese. The results were scale-dependent but clear. Rewriting high-quality data delivered a solid 3.4 NPM boost at 7B scale, while rewriting low-quality data only managed 0.5. At the smaller 1.1B scale, unmodified low-quality data performed comparably to rewritten high-quality data. The takeaway seems to be that synthetic rewriting works best as a multiplier on already good data, rather than as a magical way to rescue poor datasets. This has important implications for anyone doing continued pre-training in non-English languages. Finally, two papers dive into how models express and evaluate their own confidence. One mechanistic interpretability paper shows that calibration and verbalized confidence are encoded linearly but in surprisingly orthogonal directions within the model. When you prompt models to reason step by step while also verbalizing confidence, you actually create a reasoning contamination effect that worsens miscalibration. The authors propose a two-stage adaptive steering pipeline that substantially improves the alignment between a model's internal confidence and what it says out loud. A separate paper introduces a Type 2 signal detection theory framework to measure metacognitive efficiency using meta-D and M ratio. They show that metacognitive efficiency varies dramatically across models even when raw accuracy looks similar, and that efficiency is highly domain-specific. Temperature mostly shifts decision criterion rather than sensitivity. Perhaps most interestingly, AUROC2 and M ratio produce completely inverted model rankings, demonstrating they're measuring fundamentally different things. Let's pop the hood for a moment on that pruning paper because the representation hierarchies insight is genuinely useful for practitioners. Everyone talks about pruning like it's a simple switch you flip. In reality, it's a story about three different representation spaces reacting differently to the same perturbation. Embeddings and logits are remarkably robust. The danger zone is the nonlinear jump into probability space where small errors get amplified and then accumulate across every token in generation. This gives you a clear decision framework. You can be quite aggressive pruning for embedding-heavy workloads or single-step classification tasks. You should be much more cautious with long-form generation where those compounding probability errors matter most. The gotcha that keeps biting teams is assuming uniform robustness across the entire computational graph. Always measure perturbation effects separately in embedding, logit, and probability spaces for your specific workload. All right, here's what you should actually try this week. First, take a small OpenWE IT model between 1.2B and 8B and fine-tune it on your own domain screening or transcription data. The returns can be dramatic even with relatively modest datasets. Second, audit any clinical or semi-structured interview models you run. Check whether they're exploiting consistent interviewer prompts rather than learning from participant language. Third, when considering pruning, run the representation space analysis. Measure stability separately in embedding, logit, and probability spaces for your actual tasks. Fourth, experiment with MoFA-style LLM reasoning for feature selection in your industrial ML pipelines, especially where you face both constraints and limited labels. And finally, start evaluating your model's metacognitive efficiency using M-ratio in addition to standard calibration metrics. You might discover that your well-calibrated model still doesn't know what it doesn't know. On the horizon, expect more sophisticated speaker-aware and time-localized evaluation methods. ODS in clinical conversational AI, continued exploration of synthetic data quality multipliers across languages, deeper mechanistic work on verbalized confidence and reasoning contamination, and broader adoption of Type 2 signal detection frameworks for measuring true metacognition. Before we go, keep an eye out tomorrow for more papers exploring speaker-aware evaluation in CLI. Nicole Conversations, that's models and agents for today. If you found this useful, share it with someone who's trying to keep up with this whirlwind and subscribe so you don't miss tomorrow's update. The AI world moves fast. We'll help you keep up. See you tomorrow. This version sits comfortably in the 10 to 13 minute range while adding meaningful depth, context, and deep practical perspective to each story without introducing any new ones. This podcast is curated by Patrick, but generated using AI voice synthesis of my voice using ElevenLabs. The primary reason to do this is I unfortunately don't have the time to be consistent with generating all the content and wanted to focus on creating consistent and regular episodes for all the themes that I enjoy, and I hope others do as well.